In today's lecture, we're going to talk about section 1.3, which is the fundamental theorem of calculus. We have four main goals today. We want to cover the mean value theorem. I'm going to review the antiderivative definition, and we'll talk about indefinite integral. We're going to cover fundamental theorem of calculus part 1 and 2, and then we're going to compare differentiation with integration and stuff like that. Okay, so the first theorem that we're going to cover today is the mean value theorem for integrals. So this theorem basically states that if we have a continuous function on a closed interval, there is a point inside of that interval that takes an average value. So what does that mean? Let's look at the actual theorem here. So if we have a continuous function f on an interval a to b, then we must have a point in this interval such that the image of this point is just the average function, like the average function that we talked about in the last video in this section 1.2. So this theorem could also be written as the indefinite integral from a to b for f of x is just f of c times b minus a. So technically I'm just cross multiplying here and getting the value of the indefinite integral. Oh, the definite integral, sorry. So let's do an example. We want to find the value c such that f of c is equal to the average value of this function. So remember from last time, the average value of a function is just 1 over b minus a, the integral from a to b of my function. But this is just a definite integral which represents an area under a curve. So I can easily just graph this curve of my function f So since I have x plus 1, I know that I'm going to graph the line y equals x, and then I have a shift upwards by 1. So if we graph it, it's going to look something like this. So now this is an x-intercept, so this is just -1, because if you find an x-intercept, you just equal y to 0, and if 0 is equal to x plus 1, you just subtract, you get x minus 1. Okay, and I want to find this area under the curve from -1 to 3. So this is -1, this is 3, which means I want to find this area here. But this is just a triangle, so my area is just 1/2 times the base times the height. So 1/2 times this base has distance 4, right? Because 3 minus -1, this is just 4. And then my height of this triangle is just the y value when x is equal to 3, which means I'm only finding f of 3. But since my function is just x plus 1, f of 3 is just 4. So I'm multiplying by 4 again. This is just 8. Okay, so I found the area, and we said that this area is equal to the integral from -1 to 3 of my function x plus 1 dx. Then the average function, or the average value of my function, is just 1 over 3 minus -1 times 8. If you simplify, you're going to get a 2. Okay, so now we found the average value using the mean value theorem. the mean value theorem, I know that there exists a c that belongs to -1 to 3. This symbol, it means belongs to, such that f of c is just my average function. So now f of c is just plugging in c, so this is c plus 1 is equal to 2, then c is 1. So there's a proof for this theorem in the book. You can read it through. If you need any more explanation about it, email me and I'll explain it to you. But it's not that important. So the reason why the mean value theorem is important is we're going to use it to prove fundamental theorem part 1 and 2, but also I'm not going to prove that. The proof is in the book. You can read it through and ask me any questions about it. So now let's start reviewing the antiderivative. So the definition of an antiderivative is a function f capital is an antiderivative for another function f small if the derivative of this function is equal to that function for all values of x. If I want to write like a general form for the antiderivative of my function f, I can write it as f capital plus c, where c is just any constant. Okay, so let's do some examples. So I want to find the antiderivative for f of x is equal to 5x to the 4th. So let's think about it. I want to find a function. If I derive it, I get 5x to the 4th. So let's try this. If I take the derivative of x to the 5th, I know using the derivative rules, this is just 5x to the 4th, which means that x to the 5th is my antiderivative. So if I take f of x capital to be x to the 5 plus c, this is the antiderivative of my function. So it's all about finding something. If I derive it, I get to the original function that I want to find the antiderivative for. The second example, let's try and take the derivative of cosine. Would that work? Let's see. So what's the derivative of cosine? We know from the table is negative sine. But my function that I want is just sine positive. So to fix this problem, how about we take the derivative of negative cosine? So now the derivative of negative cosine is just positive sine, which means that I can take my antiderivative to be just negative cosine x is the antiderivative of g of x. And lastly, let's try f of x to be equal 1 over x. Let's try and find the antiderivative. So here, also from the rules of derivatives, let's try and find the derivative of ln of x. If you know the rule, this is just 1 over x, where x is bigger than 0. But how about if I take the derivative of ln of negative x, where x is less than 0, which means it's possible to plug in a negative inside of your ln here, because x is negative, so negative times a negative, that's a positive, so we don't have any problems here. And if you find the derivative, this is just negative 1 over negative x, which is 1 over x, which means I have two values that gives me my function f. So to fix this, we gotta think about the absolute value. So if I take the derivative of ln, but for the absolute value of x, this is always 1 over x, which means that my antiderivative is 1 over, it's my ln of absolute value of x plus c. And you can try it with any different example. Just think about, like, I want to find a function. If I derive it, I get to the original function that I want to find the antiderivative for. Okay, so in the previous videos, we talked about definite integrals. How about indefinite integrals? You might have learned this in Calc 1. I'm not sure. That's why I want to review it real quick. So the indefinite integral, it's the same exact thing, but without bounds, without my lower and upper limit. And it's called an antiderivative. So the indefinite integral is an antiderivative of my function. So if we want to write like a general formula, the indefinite integral for my function is just the antiderivative plus c. Okay, so this is a table with all of the main indefinite integrals. Also, the indefinite integral is important because if you can find the indefinite integral for any function, you can easily find the definite integral for that function. So let's look at this, for example. So here I want to find the integral of x to the n dx. So you want to find the function. If you derive it, you get x to the n. In other words, I want to find my antiderivative. So that's why the integral of x to the n is just xn plus 1 over n plus 1. Because here, if you find the derivative of this is just n plus 1 x to the n plus 1 over n plus 1. When you simplify, oh sorry, this has to be n because you subtract 1. This is just x to the n, which is the function that I want. So make sure to know these rules very good. Memorize them because you're going to need them. Also, indefinite integrals have the same properties as definite integrals. So I can distribute it if I have a plus or a minus. If I have a constant k, you just take it out, find the antiderivative, and multiply. Okay, so let's do examples so we'll understand how things work. So now the first thing here, since I have addition, I can distribute it using the properties. And then I'll apply the rules for indefinite integrals for each part separately, or if I want to find my antiderivative. So now the antiderivative of sine is just cosine plus, this is a power, so when you integrate x to a certain power, you add 1 and you divide by the new power, and plus c, since it's an indefinite integral. So this is just cosine plus x cubed over 3 plus c. Now the integral of secant 10 is just secant cubed plus c. And we always integrate in the same variable. So if you start with a function in terms of u, you should get an answer in terms of u in the end. Okay, so here in number 3, it doesn't look like something from the table here. So sometimes I need to simplify or distribute or do something before I find the integral directly. So here I can distribute my numerator, and I get these. Then using exponent rules, this is just the integral of x plus the integral of 3, which is x squared plus 2, x squared over 2 plus 3x plus c, all using the power rule for the indefinite integral. Okay, now here I want to use the rules of exponents. Since I know that the square root is just an exponent to the 1/2, using the power rule where I just add 1 plus c. If you add 1/2 to 1, this is just (3 over 2 over 3 over 2). And you can simplify it into 2 over 3, the square root of x plus 1 cubed plus c. And lastly here, I'll distribute using the exponent rule here. You add 1 to the power and you divide by the new power. And the integral of e to the x is always e to the x using the rules. Or if you want to think about it, oh, if I derive e to the x, I get e to the x, so e to the x is just my antiderivative plus c. Okay, so like if you look here, these are pretty basic functions. By the end of this chapter and going into chapter 2, we're going to develop methods and techniques where I can integrate almost any function using different techniques and methods. Okay, so that's the indefinite integral in general. For definite integral, we're going to use the same exact rules, but in the end, we're just going to plug in the bounds using this formula. So if I have a definite integral, once I'm able to find my antiderivative, I'm just going to plug in my bounds. We're going to talk about this more once we get to the fundamental theorem of calculus part 2. So this is just a quick fact to keep in mind for now. Okay, so let's start with our second theorem for this section, which is the fundamental theorem of calculus part 1. So here, if my function is continuous over a certain interval ab, and my capital function f here is defined as a definite integral, I can easily find the derivative by just plugging in x inside of my integrand. So here, as you notice, my bounds are always a constant a, and the other bound is a function in terms of x. So you just plug in the value x inside of your integrand, and that would be your derivative. So let's try the following examples. If I have my function h of x to be the integral from 1 to x of 1 over t cubed plus t squared dt. Simply using the first theorem, the derivative is just taking your function and plugging in x. That's it. So this is my function. Instead of the variable t, I just plug in x. And be careful, the bounds here are a constant one and just x. So you just apply it directly. Similarly here, if I want to find the derivative of this function here, we're going to apply the same exact thing, but be careful. We have different variables. So here, I'm going to take the integrand and I'm just plugging in u. So this is just u cubed plus 1 over u plus 2. That would be my derivative. That's it. Okay, now for the third example, we need to be a bit more careful, because if you look at the bounds, although 1 is a constant, but my upper bound is x squared. So I need to do some kind of substitution before I apply the theorem directly. So here, let's substitute my upper bound by u of x, for example. Then my function is going to be in terms of x. And I want to find the derivative using the theorem. I'm just going to take my function and apply u of x. But here, I kind of want to apply the chain rule. Since u is a substitution in terms of x, I want to multiply by the derivative of du over dx. So this part here is just using the fundamental part 1. But here, it's about chain rule or substitution. So now this is sine of x squared multiplied, what's the derivative of u in terms of x? I'm just going to derive it directly. So it's just 2x times 2x. So this is just 2x sine x squared. So it's applying the theorem directly. Just be careful that if you have different bounds, you need to do some sort of substitution and multiplying by the derivative when you apply the theorem. Now for the second part of this theorem, we have the same exact condition. My function is continuous on a closed interval AB. But here, I want to evaluate a definite integral. So it's pretty easy. I just want to find an antiderivative. Once you find the antiderivative, the value for the definite integral is just plugging in the upper bound into your antiderivative and then just subtracting your antiderivative at the lower bound. So some notes here. This theorem basically just want you to find an antiderivative, then plugging in the bounds to find the value of the definite integral. That's it. Okay, so some notation. You already saw this in the previous page. So if I have f of x and this kind of line here from a to b, this means I want to plug in these into my function here. So this is just upper bound minus lower bound. This is always minus. So to connect the antiderivative with differentiation, an antiderivative is just a function that can be differentiated to get the original function that we started with. That's it. That's a fact here. Okay, so let's see how we're going to apply the second part of the fundamental theorem. If we want to evaluate these definite integrals for these functions at certain bounds, how would we do that? We're just going to find an antiderivative, but finding an antiderivative is equivalent to finding the indefinite integral for that function using the rules that we've talked about before. So here, if I find the indefinite integral for the first part, we can just distribute, then using the exponent rules, where I add 1 to the power, then divide by the new power. Similarly for the second part, I'm adding 1 to my power, dividing by the new power, then plus c. So this is going to be my antiderivative f capital. So applying the fundamental theorem of calculus part 2, the definite integral from -1 to 1. So this is my antiderivative. It's just going to be f capital, which is my antiderivative at the upper bound, minus the antiderivative at the lower bound, and I'm just going to apply them here. So this is just 1 cubed over 3 plus 1 squared over 2 plus c minus negative 1 cubed over 3 plus c, which is 1/3 plus 1/2. Now these c's cancel out since I have a minus. Then negative 1 cubed is just negative 1 again. So negative times negative, that's positive. Then positive times negative, that's negative. So this is just 2/3. Similarly, for the second example, I want to find the indefinite integral of x to the negative 5 dx. So this is my antiderivative. Once you apply the power rule, you add 1, you subtract, you add 1, you divide by the new power plus c, and this is my f of x, which is the antiderivative. And then fundamental theorem part 2 tells me that the definite from 2 to 6. Upper bound minus lower bound in my antiderivative. So 5. Oh, it's not 5, it's 6, sorry. Then minus the lower bound. Okay, and similarly, c's cancels and you get something. So if you notice here, since I'm always subtracting upper bound minus lower bound, if I have this constant c, it's always going to vanish. So this is what we get from this note. We don't have to include the term plus c in the antiderivative, because in the theorem here, it does not tell me anything about having any conditions on my antiderivative. It could be anything. So it doesn't matter what value of c I take. So what if we take c to be equal to 0, just for convenience, instead of like writing c over and over again, knowing that we're gonna cancel them out from upper and lower. So we're just gonna take c to be equal to 0, and that would be my antiderivative. So let's apply it for the third example here. I'm going to find the integral from 1 to 5 of this function here. Again, I want to find my antiderivative. Finding an antiderivative is equivalent to finding the indefinite integral of my function. We're going to distribute. And then using the exponent rules here, this is just x to the negative 2, sorry. Then x to the negative 3. Applying the exponent rule, which tells me that this is how we integrate. This is just negative 1 over negative 1 plus x negative 2 over negative 2 plus c. Now, like we stated, I can just take this c to be 0 in my antiderivative. So my f of x, which is the antiderivative, could be just negative 1 over x minus 1 over 2x squared without taking any value of c. I'll just take it to be 0. So now applying the theorem, this is just going to be f at 5 and 1, where f is my antiderivative, and you just plug in the values. And you evaluate, and that's it. Okay. So technically these are like the main ideas that we need to cover in this section. You can do these problems in homework 1. Okay, I just want to cover an example that I think it's interesting, which is like an application for the fundamental theorem that we've talked about and the antiderivatives. So if we have two cars that are racing and we want to see which car goes further after 10 minutes. If the first car has velocity t squared plus t squared minus 5t, and the velocity of the second car is cosine minus t plus 1, and we want to see which car is going to win. So here, remembering the fact from last video where the distance is just taking the area under the velocity function, but taking the area under the velocity function is just my integral. So if I evaluate the integral of my velocity, I should get my distance. So here, I want to find the integral for each car to see which car traveled further. But I need to find my bounds. So to find it, you're going to look at, I'm going to start at time 0, obviously. But I'm going to stop after 10 minutes. Because after 10 minutes, this is when we decide whether car 1 or car 2 won the race. And similarly, I'm going to take the integral from 0 to 10 of the velocity of my second car. And find it. So here, we're going to apply the same process like we did before. I want to find my antiderivative. But this is equivalent to finding the indefinite integral. Using the rules, this is just t cubed over 3 minus 5t squared over 2 plus c. So my antiderivative is just taking that as a special case with c equals 0. Now using the fundamental part 2, you just apply the upper minus lower bound into this function. And subtract the lower bound, which is just going to be 0. If you actually evaluate it and round it, this is almost 83.3. Now so that's the distance traveled by your first car. The second car, to evaluate this using the fundamental part 2, I want to find my antiderivative. So let's find the integral here. Using the rules, this is just sine so my antiderivative, this has to be t. You just take sine of t minus t squared over 2 plus t. Now we can apply the theorem where I do upper minus lower bound. So this is just sine of 10 minus 100 over 2 plus 10. And if you round, this is going to be equal to almost 60.17. Oh, this has to be positive, sorry. Because if it's not positive, it's going to be negative, which is not correct because we can't have negative distance. So if you can see, the distance traveled by the first car is larger, which means that the first car won the race. If you have any questions, please email me and I'll explain more. good luck with everything, and yeah, just keep in touch and feel free to email me whenever you want.